Thank you, everybody, for joining. We are going to get right into it today. So this is an enormous subject, especially to attempt to tackle in about 40 minutes. So we're just going to dive right in. As far as who this talk is geared for, it's really for people in the enterprise. If you're one of those folks, you're probably just beginning to kind of hear it from vendors, and you may be also hearing it from your board or other executives. But an increasingly common assertion is you need to become an AI-driven SOC, or you need AI-driven security. So in the next 40 minutes or so, we're going to break down where statements like that really should apply, and where statements like that are actually causing some security practices to get a little bit off the rails. So let's start today with an exercise. Imagine, if you will, a world in the near future where AI drives cars without human assistance. So the AI is capable of understanding the physics of the car's movement and the boundaries around road infrastructure and methods for interpreting, various markings and predicting outcomes based on surrounding, static and sometimes erratically moving objects. But it's still able to make decisions and safely deliver you from point A to point B every time. Now, this should be a really easy exercise because we basically have that technology today, right? So now imagine a world, we can say also in the near future, where AI can replace a child or a family member, potentially without you even knowing. There's a Steven Spielberg film on this, right? That was actually called AI. And even though Hollywood has kind of made that idea come alive, it's still really difficult for most of us to imagine that because, frankly, as we know, there just isn't technology out there that's actually capable of that. Plus, that would be some actually pretty creepy software. But when you compare these two scenarios, it's easy to start to see that there are applications of AI that are good or believable even, and possible, and there are applications that are really maybe not so good or believable. And what's important to understand here is that holds true when you're talking about AI in InfoSec also. So this talk is probably going to be a little different from most you've encountered about this subject. Rather than give you an overview of algorithms and technologies, we're going to try to answer a really important but often overlooked question. That is, what problems in InfoSec are good challenges for AI and which are not? So I personally come at this subject, I think, from a little bit of a different perspective. My career in InfoSec started about 18 years ago when I got a lucky break, that I think is a lucky break, from Ron Gula, who was the original creator of the Dragon IDS. And I was invited to join his small team to do threat detection research. Since then, I've been focused either on incident response types of engagements, and have actually had the awesome fortune to work with some absolutely brilliant people on some of the most notorious and publicized cases out there over the years, or I've been doing product-focused research and development. In terms of AI, I started working intimately with it when I joined Cylance, actually the day after the company was founded, about 6 years ago, and have worked with an array of data science projects in different contexts here where I'm at now at Awake over the past 3.5 years. But one thing's remained constant in my role on AI-focused projects. So I'm usually part of the process that is there to challenge the models, right? So trying to discover what the models are not telling us, or trying to identify the silent failures, and really ultimately to help identify better features or better strategies for ultimately achieving better results. So because of that, today we're not going to perform an inventory of today's most popular machine learning methods and highlight the pros and cons of, say, random forest versus regression. Instead, we're going to focus on the other side of the question, and that is, what types of data lends itself well to AI-based methodologies, and therefore, what types of InfoSec challenges are best addressed by it? And honestly, for my own well-being, I have to throw out another disclaimer here, which is I intended originally part of this talk to be focused on the difference between AI and ML, but the data scientists that I spoke with leading up to this talk were really convinced me to basically abandon that part of the subject, really saying that, a few years ago that may have been a relevant argument, but at this point, almost everybody uses the terms interchangeably, so there's really no point arguing about those kinds of semantics. So for the first time publicly, I am using the term AI in the same way the industry is using the term, but please know in my heart I mean ML in a lot of cases. Anyways, so let's get going here. Let's start with the most fundamental of questions, and that is, what is AI within the field of information security? And the reason that we need to ask a question like this is because, while the fundamental components or techniques used by AI approaches across different industries are extremely common, what AI encompasses across those different industries can be considerably different, right? So think about the example that we referenced just a few minutes ago, and really one that's like one of the crown jewel sort of reference cases for AI in industry, and that is autonomous or self-driving vehicles. In the case of a self-driving vehicle, you can create models for what other cars look like and how they move and things like that. And this is like really, really important. Ultimately, because there are rules governing those objects. And this is a concept we're going to come back to again and again over the next half hour or so. So what people look like, what other vehicles look like, what strollers look like, what bicyclists look like, right? Like all these things, and critically, the characteristics and limitations governing their movements. So really, and this applies to, signs and roads and markings and in actuality, right, all objects in the natural world that a car moves through. But it could really be argued, I think, that it's not actually the AI algorithms and the models that are the defining feature of AI in autonomous vehicles, but rather the data set. So another way to think about it is, in an autonomous vehicle, you have ultrasound sensors, and you have LiDAR, and camera, and radar, and other types of sensors, right? And all these sensors are constantly creating a vast array of information. Many different, and importantly here, many different data points about the same object as scanned by different technologies. So each of these sensors are, constantly creating a multitude of features about all the objects surrounding a vehicle, which, as we'll see later in this talk, is extremely important for a successful AI implementation. But we do not have those same conditions in InfoSec. We don't have many different sensors producing lots of different detailed data with the confidence of ground truth, and we're going to come back to that concept again and again, ground truth. But creating basically detailed data about all the or objects of interest as seen through a multitude of lenses. Okay, but first, let's step back and ask, why is there so much hype around AI, especially in InfoSec, right? And really, and very, stated very simply, AI is capable of sifting through and finding patterns and relationships in far more data than humans can examine. While at the same time, and I think more excitingly, combinations of patterns that are way too subtle and a lot of times just way too complicated for humans to have identified in the first place. And this is exactly the problem we have in InfoSec. Too much data, too few people to examine it, right? So yes, definitely, AI is absolutely another tool in the InfoSec toolbox that has much needed advantages given current InfoSec realities. So, in other words, there's a lot to be hopeful about. But you could ask, well, what's the holdup out there? And a good way to start thinking about that question is in terms of rules. So just look at the cases where AI has had proven success. So if you think about chess playing AI, or you think about self-driving AI, and all the other really compelling AI applications you could probably think of, there's one thing that they will generally all have in common, and that is they operate in a space that is tightly constrained by rules, and where all the key components or all the key players in the system basically adhere to those rules. And as we're going to see as this unfolds, there's a little bit of bad news there, which is we actually don't have a lot of that in InfoSec. We certainly have some of it, and we'll look at those cases too, but not a lot. So at this point, I can imagine people already getting a little uncomfortable with some of these assertions and thinking, well, wait. Unsupervised learning learns by itself, and then you have examples like Google's DeepMind, which learned what a cat is simply by surfing the internet, right? So if these things are possible, surely computers should be able to identify malicious actors without a priori human knowledge now, or at least pretty soon, right? And yes, it's true. So there are indeed several unsupervised AI techniques that work on data to create groups or divisions in data that can be studied and interpreted by humans or other systems. And it's true that these do not require human-labeled data in advance to operate. So in a sense, they learn on their own. And in fact, actually at Awake, we used several of those techniques to automate the type of work that was previously very tedious and very error-prone for people, and typically the types of things that only really sophisticated analysts were previously able to do. However, the most commonly marketed use cases for AI in InfoSec generally involve something different. Usually involve the algorithms doing what we could call presenting results to the user of the system, right? So you could think about the results being, this is a good file, or this is a bad file, or this is lateral movement, or this is C2 activity, right? In all those cases, the system is labeling the data and presenting results, basically presenting labeled results. And the same applies to this is a good chess move, or this is a bad chess move, or the vehicle should keep going straight, or the vehicle should swerve a couple feet to the right because of that stroller, right? All of those things are examples of ultimately choosing labels, presenting results, and in some cases, taking an automated subsequent action based on that, right? But importantly, there are two significant challenges to achieving all those really impressive results that we were just sort of referencing as example there, right? In both cases of unsupervised and supervised approaches. So one is the ability to establish ground truth, most commonly done through labeled data with supervised methods, but is also required in other ways for unsupervised methods. And the other challenge is something that I tend to refer to as discernibility. Okay, so in an InfoSec world without AI, which is to say before a few years ago, vendors and enterprises needed expert humans to validate detection technologies and create basically an ever-evolving set of rules for detection within those systems, and then do the work to manage and curate those changing definitions over time. Now, in a world with AI, we've partially kind of eliminated that requirement, while actually introducing some others. So if you're not going to have an expert human create a rule or heuristic for a sample in question, then you need lots of samples for the computer to figure out what that rule or heuristic should be, or to be more accurate here, right? In the case of computer, a neural net might be an example of replacing what was previously a rule or heuristic that the human derived. So the first requirement to use AI is the availability of labeled data that covers the full range of use cases or variations that you intend to identify. So, of course, you can kind of think that you notice that the subtext here is that, well, the labels actually still require human subject matter experts to create those labels in the first place. And, same applies, though, in different ways to the unsupervised methods of validating. And usually those are the same people who were previously writing rules or signatures. And as you might expect, that step is also subject to a lot of the same types of human error as previous non-AI-based methods. But look, even if you ignore that, which honestly I think you can for a couple different types of cases, the practical problem here is access to a sufficient number of samples that cover a meaningful range of real-world threat cases. But to me, really, there's one more issue that is more insidious and really a lot more subtle as it applies to AI in the real world. And it's what I refer to as discernibility. And this is where we start dissecting issues around the importance of those ground truth rules that I referenced earlier, right? So as I'm sure most people on this webinar have experienced, a lot of AI discussions tend to focus on algorithms and models, right? So you've probably heard multi-class classification versus regression, or subjects like that may sound somewhat familiar. But unfortunately, the chosen data source to be analyzed by AI is frequently ignored, and really, more importantly, the features of that data source. And this is critical because there's characteristics of the data set itself that are just crucial for the proper functioning of AI. So a good way to get to the heart of those issues is to think about them in terms of questions you can ask about the technology you're examining or the technology you're working with. So to me, some of the most potent examples include the following questions. And in a moment, we're going to apply these questions to a couple different use cases so you can see how to utilize these concepts to your advantage. But first, just to run through them, right? How will the data set change over time? Is it possible for the data format or structure itself to change? More importantly to me, I think, how can the values within those structures change over time? I mean, really getting to the heart of it, can the meaning of those values change over time? How many sources manage possibilities for change or could introduce change in other ways? And then what is the rate of change for each of the characteristics above? And finally, how closely will the training data match enterprise data over time? And so I believe that that second to the last question actually dictates how successful an AI implementation can be, and that the last question dictates how relevant that solution will be for your environment. All right. So let's get to the fun part and start applying these questions to a couple use cases to see what we can start to learn about AI applications here. So first one, right? With hundreds to thousands of new malware samples discovered per hour in the wild globally, this is a problem that humans just can't scale to handle, but it's actually a fantastic problem for AI to tackle. So to me, the reason why companies like the folks I know at Cylance, have been so technically successful with their AI implementations is because they focused on InfoSec challenges that have optimal answers to the questions that we just listed out. So as an example, and in the context of this problem right here, let's consider the case of using AI to analyze files to determine if they're good or bad. So our first question, How will the data set change over time? And let me throw out here, right? We only have a total of a little over a half hour or 40 minutes to talk about this. So we'll focus this part of the conversation on executable files. I am happy to talk with people offline about other types of data, but just for the sake of conversation here, we're going to think about executable files. All right, how will the data set change over time? The structure, the file structure for executables has had a very, very small number of changes over the nearly 30 years it's been around, which means models created around them remain relevant for a really long time. So that's good, right? Okay, our next question. Is it possible for the data format or structure itself to change? So in this case, the answer is closely related to the previous question. The structure of executable files does not significantly change over time, right? In order to provide backwards compatibility with some actually pretty old operating systems at this point, or more technically, the loaders within those operating systems. But the important point here is we do not experience significant change over time. Okay. Just even more importantly, in a lot of cases, right, how can the values within those structures change over time, and really get into the heart of it, can the meanings of those values change over time? And this is great. This is great for this case, right? The interpretation of values within most of the operational fields within an executable, they're very tightly defined and controlled. So whether you're an attacker or not, there is a very narrow range of data types that you could put into most fields without negatively impacting the ability to actually execute that file without it crashing, meaning that the data the model is trained against and the meaning of that data it's not likely to change in relevant time horizons. Next. How many sources manage possibilities for change or could introduce change in other ways? In this particular example, technically speaking, the executable specification is not controlled just by Microsoft, but in practice, we can basically say there's a single entity that controls the specification and makes significant changes. So also a good thing, as we'll see when we start to contrast this to other non-ideal examples. What is the rate of change for each of the characteristics above? In this case, and we've kind of started pointing this out already, very, very slow. And then finally, how closely will the training data match enterprise data over time? And because there are a large number of ways to collect a very large numbers of binaries that are really a lot of the same binaries that you find in a variety of enterprise networks, that means that the training data tends to be a pretty good representation of what you encounter in the real world, right? So if you're connecting the dots as you're following along here, you may start to notice kind of a striking similarity between the threat analysis case of using AI to analyze files and the self-driving car example, we talked about it a few times now, right? And in both cases, and this is important, the important characteristics of the data being analyzed is largely static, right? So with self-driving cars, the physics governing how cars and other objects move does not change. The rules of the road, markings used on the road and for signage, and really just the general features of the physical areas in which a car moves are, relatively speaking, consistent. And with executables, the features of the structure and the format and the rules for interpretation are also, relatively speaking, consistent. So also extremely, extremely importantly between the two, the rules governing each domain are obeyed by all players. And that's important enough that I should repeat that, right? So the rules governing each of those domains are basically obeyed by all players, right? So with self-driving cars, other drivers, yes, they do behave erratically, but they cannot bend the laws of physics no matter how much road rage they get, right? And the same applies to the case of analyzing executables. While attackers can do things like pack an executable or modify it in a lot more subtle ways that actually makes it very, very difficult to reverse engineer them, in reality, they actually have very little room to make significant modifications to the executable, because the reality is that changes that are too significant will cause the program to fail to load or to just crash too easily, right? So attackers can make executables very hard to reverse engineer, but the executable still needs to execute. So this starts to kind of illustrate really that critical importance of ground truth and strictly followed rules. So, in terms of Goldilocks and the theme of this presentation, that porridge is just right. Now, I'll describe what you're seeing here in just a few moments. But for the sake of conversation, let's assume you want to discover a very common type of threat case encountered, or I should say case that's encountered in insider threat investigations, right? So you have a user who's an employee of your company, and they take files that are legitimately and normally emailed to them. And so we're not talking about this person going into data center, going into file shares and trouncing all over files. We're talking about just files that are normally emailed to them, that you may email to them, but then they use some other website to send those files out. And you want to discover this kind of activity. So the first problem here is that it is not possible to obtain a large enough number of samples of that type of activity to train against. Secondly, and starting to sort of peel back some layers there, right? People's normal justified activity and normal justified behaviors change just too frequently. And this is something that we've observed over the years, that people's normal justified activities and behavior change with the type of projects they're working on, or as the type of projects they're working on changes. So on top of that, there really isn't enough sensor data available. So remember, and this is important, this is something that will kind of thread through some later examinations, but remember how much sensor data it takes for a self-driving car to operate accurately enough to be considered safe, right? So all these issues begin to illustrate why modeling good and modeling bad threat behavior in the real world can be extremely error-prone in a lot of cases, right? And actually, there's kind of a secret within the industry that I think is kind of hidden within that last point. And so when you examine through that lens, you start to see why a lot of log-based, AI solutions can be useful for really a very, very limited set of types of threat cases, right? And if you think about it, between the network and endpoints and logs, like logs contain the least detailed data, and by far the least amount of data as a whole of all those available solutions. So they're basically at the opposite end of the spectrum from kind of that self-driving car example, and sometimes the results can reflect that. But anyways, the difference between the malware AI case that we looked at a few moments ago and the subversive employee case that we were just talking about illustrates how the availability of concretely labeled data for machines to learn from, or really kind of the lack thereof, presents just one set of challenges, right? But that was a bit of a philosophical example. So let's examine a type of case that we've actually seen more concretely kind of out in the market, right? Let's consider network traffic. So the characteristics or features of traffic used in models for AI-based detection usually include some combination of protocol characteristics, and if the information is available, maybe destination domain characteristics, right? And so, to make this a little more concrete, let's consider a common type of reference case, which could be something like malicious redirect chains or C2 types of examples. And here we see an example of some of that type of activity. And you know, it's worth noting that what we're looking at right here, we'll go on from this. This was not found using AI, but rather performing more of what we refer to as TTP-based searching or observation within Awake. And I'll explain the significance of that in a few moments. But just as a quick piece of context, just to explain the query that you're looking at here, this particular example was found by asking the Awake platform to show us devices in our network communicating with servers that were advertising themselves as Microsoft or Google or Facebook, yet the traffic is going to a destination that's not registered by the company that does domain-related brand and intellectual property management for those companies. So, you know, you can, as an attacker, you can try to look like Google or you could try to look like Facebook, but at the end of the day, you can't look exactly like Google or exactly like Facebook. And there you see kind of a long list of suspicious and malicious activities that were found in a real network, like literally just a couple days ago, based on that logic. Not to mention the one that we have highlighted there, you may notice, domain that was actually just registered like 10 days ago. Okay, so all of those things, all the things we just talked about, and the things that you may start to notice even on this slide when we look at the traffic related to what we were just looking at on the previous slide, all of those things can be, like AI can be used to model, right? Including how recently the domain was registered, how short the registration is, the registrar used, especially in combination with like current hosting characteristics, not to mention getting into the uniqueness and patterns of the traffic to that destination, characteristics of the client application generating that traffic, you know, the types of things that you see highlighted on this slide. So yes, you could argue that absolutely, it is definitely possible to generate models capable of flagging that traffic. And in fact, I guarantee you will see marketing presentations showing you exactly that if you have not already. I know I've seen it. I can think of a few examples offhand. So I can guarantee you'll be pitched about doing the same in your network. But here, let's examine kind of the predicted longevity and accuracy, and really because of that, the relevancy of models based on that. So let's go through our questions. First one, how will the data in the data set change over time? And so just in the context of this small example, how HTTP like request methods are used across different applications, it changes. URI structures or the data that's in URIs can change based on the applications. HTTP header field names and values are designed to change. Anybody who's been looking at the network for any length of time knows user agent strings are always changing. And really, I mean, beyond just the protocol characteristics, even the characteristics of the domains, standard characteristics for just legitimately registered domains are constantly changing. The fluidity and sometimes like downright aggressiveness of content delivery networks and an ever-growing number of internet-connected applications and more and more internet-connected devices basically ensures that change on the network and in protocols will be greater and more rapid as time continues. Okay, and this is a reality that we've been watching unfold for the past few years here at Awake, right? Like as an example, right? So just a few years ago, web traffic was pretty much primarily it was HTTP or SSL, and literally within a couple of years, Quick is now among one of the top used internet protocols, and we can certainly predict other offshoot protocols like Zero Protocol will be dominating that list soon too. So what you can start to enumerate from that is that keeping up with what's good can actually be more challenging and more difficult than trying to keep up with what's bad. And that means that the AI is constantly racing against blind spots. introduced by both good but unknown data, plus bad activity that starts taking advantage of the new but unknown good, right? And most AI-based methods for compensating for that reality can, in some cases, actually lead to more false positives than you may have even seen with signatures in similar scenarios. All right, so let's go next one. We got a whole bunch of questions on this example to get through here. So, is it possible for the data format or structure itself to change? So, in terms of the characteristics of the domain, whois structure changes slowly enough to be manageable in theory. And there's definitely an asterisk I would apply here that I don't think we're going to have a lot of time to explore, but HTTP is extensible. So yes, it is an issue by design. And make no mistake, so is SSL, right? Especially the fields used in AI applications. So there may be people on this call who have recently seen a discussion out there about using AI to find malware inside SSL or TLS encrypted tunnels. We've been doing something very similar to that actually for about three and a half years here at Awake. I can assure you it is not such the incredible feat of science fiction as it may sound. Yes, it is possible, actually very, very, very effective. But also the important point there is that those fields that allow you to do that, they change as well. All right, going on here. So how can the values within those structures change over time? Or maybe even more importantly, can the meanings of those values change over time? All right, so unfortunately, the answer here is a resounding yes, right? The interpretation of values in headers is subject to really each and every application out there sending or receiving those values. This is pretty much why RFC compliance focused security technologies largely vanished in the early 2000s. So I'm sure there's some people on this call who can like me, show their age a bit by remembering protocol anomaly detection products, right? It was a really great idea if software on the network actually followed RFCs. And as we know, it does not. Okay. Our next question, how many sources manage possibilities for change or could introduce change in other ways? Maybe this is not a worst case scenario, but it's pretty bad. And that is anyone with coding skills, anyone with scripting skills is going to introduce, they're going to be doing things on the network that introduce change there or variation. Proxies create change. Browser plugins, which are constantly changing, are also introducing change into that data. And so, there's basically what we see is there are countless possibilities here for change, and that's tough to keep up with. What is the rate of change for each of the characteristics above? So, look, we've kind of talked about this already because of content delivery networks, because of, phone apps, and really a slew of new internet-connected devices. The rate of change in this data set is breakneck. And finally, our last question, how closely will the training data match enterprise data over time? And for me, okay, this one is the nail in the coffin, right? Enterprise networks are a heterogeneous mixture of many different types of devices and peripherals and infrastructure and IoT and BYOD and all of those things, right? And so it is extremely difficult to get access to enough data to create models that work accurately across different environments, right? And with the rate of change that we previously discussed, in a lot of cases, it can be kind of a fool's quest to even try to keep up with that. So in this small example, right, you can see how it's really nearly impossible in certain cases to baseline what even good is, much less bad. And the important point there is because you can almost never achieve a high confidence ground truth reference for what is good and what, and therefore ultimately, what is bad. And so in the context of how we started this talk, about good versus not so good use cases for AI and InfoSec. What's missing in this example are rules that are consistently followed by all components or by all people, playing the game, if you will, right? In fact, look, this is, not only are the rules not followed, they're actively broken, they're actively changed constantly. And we know this to be a fact, since if you think about the way browsers work and web servers at this point in time, they're designed to take a best guess at rendering the data that's presented to them, knowing that very few people actually follow the rules or actually follow the RFCs for those most common protocols. So in terms of our Goldilocks analogy here, this bed is just too uncomfortable. All right, so augmented intelligence, the other kind of AI, rather than our artificial intelligence, let's talk a little bit about augmented intelligence, which I think has a really promising future in InfoSec. So if I haven't said anything controversial yet, this next part might be that. So that one way of looking at AI and kind of thinking about where it fits and how it can fit into the entire InfoSec toolbox is to sort of take the point of view where you could say, AI is actually just like signatures in many ways. So both approaches to identifying patterns have pros and cons, right? We need to be realistic about that. Both require a lot of work by humans to make them accurate enough to be usable. Both of them require really just as much work to manage and maintain them over time, to keep them relevant beyond the day they were created and seem to be accurate. Both have false positives. Both have false negatives, right? The reality is certain types of threats and certain types of activities are probably better identified by one as opposed to the other. And honestly, I think I could fill probably a 1-hour presentation just right here, just on this part of the discussion. The point here in our limited amount of time is to say that actually AI signatures can be similar in a surprising number of cases. Again, not all cases, but certainly some that you're familiar with and are currently referenced out in the market. And we'll kind of come back to the significance of that towards the end. So it's also important to kind of to pull back from that point of view we were just focused on there. There's also a substantial difference between not just AI and signatures, but AI and all the methodologies that preceded it. Not just signatures, but even the protocol anomaly detection or heuristic-based, methods and behavioral analysis, things like that, right? And that is, AI can directly contribute to making humans more effective in ways that none of those previous methodologies could ever do, right? So AI is actually capable of taking on workloads that signatures or protocol anomaly detection or heuristics or any of those other methodologies just cannot do effectively. And if that work is required to complete a workflow or make an important decision, and if the work in question is normally tedious or error-prone, which means, in turn, right, it makes the work for you demoralizing and inefficient and actually a lot of times, a surprising number of times, incorrect, then that's a perfect opportunity for AI to pre-process the data so humans can focus on doing what humans do best, which is identifying and making decisions about justified versus unjustified activity. And really, this is exactly how and exactly why we're using AI at Awake. So we can see a great example of what I was just talking about here, just in this small part of the Awake UI, right? So I'm going to step through a couple elements of this screen, and you can see quite a few examples of AI basically augmenting human intelligence, and human intelligence beginning to augment AI. So in the top left corner here, what's happening is the system is taking traffic off the network. So packets, ultimately packets. And without looking at log sources, without looking at anything else, simply by only looking at the packets, it's determining what system that network traffic belongs to. And then once it's created kind of a fingerprint, or once it understands what that system is, it'll follow that system around the network. So that system could change IP addresses, and it can move to different parts of the network. And again, without logs, without any other reference source, we're able to ultimately understand that this is the same system. It's just changing IP addresses. And there's a set of AI-related technologies that are involved in doing this, and part of also what you see there is we ultimately can identify what that system is in a lot of cases. In this case, if you can see it, that's where we're actually looking at an Xbox. Then in the next little section here, we start getting into similarity analysis. So there's a different set of algorithms that are running and trying to figure out, basically, clustering or grouping, who's most similar to these devices and these systems or these people that we identified by extracting and processing just the data on the network. And there's a wide variety of use cases for that, can really accelerate investigations into some really interesting types of threats, actually. But just sort of continuing on here, there's also cases where we can use that data to do what you see here and start to identify interesting anomalies, right? And so we can, when we say anomalies, in this case, we mean something much bigger than the way you've probably seen that term referenced in the past. So not understanding how this Xbox is different from all the other devices on your network, like Windows laptops and Android phones and Macs and all those. Of course the Xbox is going to be different from all those things, but also asking the question, how is that Xbox different from, if there are other Xboxes on the network, how is it different from those? And what we see here, and it's partially redacted, but what we see here is, oh wow, okay. Well, I just got the time warning. I didn't realize we've gone that long. So what we see here is that this Xbox is actually using domain credentials, and domain credentials that are being used on a few other systems, and so that's highly alarming to us. And then we start to see the human-based information that's been added to the system, which in turn can help feed the AI. I'm just going to fly through it because really, let's get to the part. Here's the part, we want to focus on things that are going to help you. Whether you're evaluating vendor marketing claims or thinking about spinning up your own internal effort, here's a few questions to make sure, you're really, cutting through the cruft and considering the right tool for the job. First one. What threats does or will the AI approach detect that wasn't previously detected already? Look, a big problem with AI is, for lack of a better analogy, it could be like bringing a gun to a knife fight. Like creating an AI-based system is a significant undertaking. And in InfoSec, we have a wide variety of cases we need to address. Ultimately, make sure that if you're bringing in some technology, it addresses a large range of cases, that you're not applying a giant patch to a small hole. And if you think about a lot of technologies you already have, you can actually apply those to a lot of cases. Why is the AI only the best way to do the job? Look, really, if it's solvable via rules, and a lot of times you'll see threats that are addressable that way, then you probably already have technology in your organization to solve that problem. And finally, in what ways does the system compensate for AI's weaknesses? Lots I'd like to talk about here, but we'll just cut to it. It's not a silver bullet. AI is not a silver bullet. Ensure that the vendor is more focused on the problem they're trying to solve for you than the AI they're trying to sell you.